In a perfectly symmetric universe, molecules should form in equal proportions of left-hand and right-hand versions, just like mirror images of each other. Yet, life on Earth exhibits a striking preference. Amino acids, the building blocks of proteins, are almost exclusively left-hand, L-chiral, while sugars in DNA and RNA are right-hand, D-chiral. This phenomenon, known as biological homochirality, presents a deep mystery in chemistry and physics. Why does nature break this symmetry, and how does one chirality dominate despite symmetric synthesis pathways? Imagine flipping a coin billions of times under perfectly fair conditions. You would expect roughly equal numbers of heads and tails. Similarly, classical chemistry suggests that simple reactions should produce equal amounts of left and right-hand molecules. However, reality tells a different story. Where does this bias come from? One possible explanation is weak nuclear forces, one of the four fundamental forces of nature. Unlike gravity or electromagnetism, weak interactions violate parity symmetry, meaning they slightly favor one chirality over another at a quantum level. Experiments suggest that this tiny bias could have nudged early prebiotic molecules toward a preference that was later amplified through natural selection. Another theory involves autocatalysis, where chiral molecules catalyze the production of more molecules with the same handedness. If even a tiny imbalance occurred in primordial conditions, perhaps due to stochastic fluctuations or mineral surfaces that preferentially absorbed one chirality, it could have been reinforced over time. Cosmic processes may also hold clues. Some meteorites, such as the famous Murchison meteorite, contain an excess of left-handed amino acids, suggesting that asymmetric physical forces, such as polarized light from distant stars, could have influenced the chemical evolution of life even before Earth formed. Could circularly polarized light from supernovae have selectively destroyed one chirality of molecules in interstellar clouds? The paradox deepens when considering that modern laboratory synthesis still struggles to produce chiral purity without specific catalysts. Why does life achieve this feat so effortlessly? Could self-organizing chemical systems naturally drift toward a chiral imbalance, just as turbulent weather patterns spontaneously organize despite chaotic conditions? This question remains at the frontier of origins of life research. The emergence of chirality could be a fundamental signature of life itself, an inevitable outcome of self-organizing chemistry in a dynamic, asymmetric universe. But here's the ultimate question. If life exists elsewhere, will it follow the same chiral preference as Earth? Or will we find alien biochemistry built from mirror-thin molecules? Symmetry in chemical synthesis suggests that chiral molecules should form in equal amounts under standard conditions, yet biological systems overwhelmingly use one form, L-amino acids and D-sugars, creating a paradox that challenges equilibrium thermodynamics. Unless an external symmetry Bokine factor is present, reactions should yield a racemic mixture, making the origin of homochirality one of the most fundamental questions in biology. Miller-Urey-type prebiotic chemistry experiments produce both chiral forms equally unless influenced by circularly polarized light or chiral catalysts, hinting at external factors in early molecular evolution. This is like flipping a coin a million times and expecting equal heads and tails, but instead consistently getting more heads without an obvious reason. The weak nuclear force, which violates parity symmetry and beta decay, could have subtly biased early organic molecules toward one chirality. Although this effect is extremely small, tilde 10 to 17 EV energy difference, it suggests a possible fundamental reason for life's chiral preference. Experimental studies indicate a slight energy difference favoring left-hand amino acids, but whether this could influence macroscopic molecular evolution remains uncertain. It is like tilting a roulette wheel by a fraction of a millimeter. While the bias technically exists, it is nearly imperceptible over short time frames. Once a slight excess of one enantiomer appears, autocatalytic reactions can exponentially amplify this imbalance, leading to homochirality. The SOI reaction, for instance, shows that an initial enantiomeric excess as small as 0.0001% can result in nearly 100% chiral purity in the final product. demonstrating that self-replicating chemical networks could reinforce a tiny initial asymmetry. This is like an election where one candidate starts with a slight lead and their popularity snowballs due to media influence, social reinforcement, and feedback loops. Astronomical observations reveal that circularly polarized ultraviolet UV light from neutron stars or interstellar clouds can selectively destroy one enantiomer over another, potentially biasing early organic molecules in space before they reached Earth. Meteorites like the Murchison meteorite contain excess L-amino acids, suggesting extraterrestrial organic matter was exposed to asymmetric radiation fields. This is similar to using a polarized lens in photography. Certain light wavelengths are filtered out depending on their orientation, altering the overall balance of light in an image. Chiral surfaces, such as quartz or calcite crystals, can selectively adsorb and stabilize one enantiomer over another, acting as prebiotic templates for asymmetric chemical reactions. Laboratory experiments confirm that L-amino acids preferentially bind to certain crystalline surfaces, enriching their concentration over time. This effect suggests that prebiotic mineral surfaces may have played a role in early homochirality. It is like a parking lot where cars arrive randomly, but certain spaces are better suited for specific car sizes, leading to a predictable distribution over time. Even if life began with a random chiral bias, natural selection would have quickly locked in this asymmetry, making a transition to racemic biochemistry nearly impossible. Since biological molecules interact stereospecifically, the emergence of lamino acid-based enzymes ensured that only one chirality persisted in evolving life forms. All known ribosomes exclusively use lamino acids in protein synthesis, demonstrating evolutionary lock-in. This is like a society choosing a writing direction. Once a culture commits to left to right or right to left, reversing the decision becomes impractical. Meteorites often contain an excess of left-handed amino acids, hinting that asymmetric cosmic processes influenced early chemical evolution. Cosmic rays interacting with interstellar dust can generate circularly polarized light, further biasing the synthesis or degradation of chiral molecules before they even reach planetary surfaces. The Murchison and Tagish Lake meteorites show up to an 18% excess of L-amino acids, far beyond random expectation. This is like planting seeds in soil with a slight nutrient bias. Some plants naturally grow better than others based on the initial environmental conditions. Although left and right-handed molecules are energetically nearly identical, small differences in solubility, stability, or environmental interactions could reinforce homochirality over evolutionary timescales. Environmental fluctuations, such as temperature cycles or pH variations, might have provided consistent selective pressures favoring one enantiomer over the other. Some amino acids exhibit slightly different solubility properties depending on their chirality, allowing phase separation that could enhance homochirality. This is like two athletes with nearly identical skills, but one has slightly better endurance, giving them a long-term advantage in competition. If life's chiral bias arose from random fluctuations, then extraterrestrial life may use a different chirality depending on its environmental history. However, if weak nuclear force interactions or cosmic polarization were the dominant factors, then homochirality may be a universal trait shared by all life in the universe. Future space missions, such as those to Europa or Titan, will analyze organic molecules to determine whether they share the same chiral preference as life on Earth. This is like visiting different civilizations and finding they all use the metric system. Either a universal principle is at work or independent histories led to the same conclusion.